Hi there, my name is Dave Glover and I'm a cloud developer advocate based in Sydney, Australia. Now I'm going to focus on the Internet of Things and more specifically around secure IoT and Azure Sphere. Now the project I'm going to talk about is what we did to bring the Altair 8800 emulator to Azure Sphere. Now, the Altair 88 emulator is an open source project and it's been ported across to a number of platforms, and we're ported across to Azure Sphere. And more specifically, and perhaps more uniquely, what we've done is we've cloud enabled the Altair 8800. Now, if you're not familiar with the Altair 8800, it was a personal computer invented back in 1974. And it was built on the second generation Intel CPU known as the 8080. And the way that you originally programmed the Altair 8800 was with these switches on the front. And there were 16 switches, and there was a 16-bit address bus and an 8-bit data bus. And you would literally program it by flicking those switches and entering data and setting the addresses. So what we've done is we've taken the Altair emulator and ported it across to Azure Sphere. And the project is up on GitHub. It's completely open source. And you'll find it on github.com/Azure Sphere Cloud Enabled Altair 8800. And in there, you'll find the Azure Sphere Altair 8800 project repo. And go and check out the wiki. And in the wiki, there is a complete description on how to write, how to deploy the Altair to the Azure Sphere. There's a brief description there about what makes Azure Sphere unique, and particularly around its focus around security. And then there is an architectural discussion about what the solution looks like. Now, the impetus behind this project was kind of twofold. One, it's kind of cool. There's a lot of interest around retro computing. But the bigger picture really was, what can we do to really push the barriers around our Azure Sphere, to find out what we could do and design and define interesting patterns that we think would be broadly useful for more day-to-day applications. So that's kind of the idea. In fact, some of the patterns that we've come out of this project are finding their way up onto the Azure Sphere gallery. So it's made up of 3 tiers. So we've got the Azure Sphere device, which is running the Altair 8080 emulator. We've got a mid-tier, which is a cloud services, which is running up on Azure. We're using IOT Central for configuring and reporting on the Altair 8800 emulator running on the Azure Sphere. We've got a Azure static web app. We're running something called an Altair web terminal, which I'll explain a bit more in a moment. And I'm also running a virtual machine. And on that virtual machine, I'm running the Mosquito MQTT broker. Now, over to the right, we've got the web terminal. And the web terminal is made up of 2 libraries. So it's a browser-based application, and we're using Xterm, a JavaScript library, which provides console capabilities, and we're using the MQTT JavaScript library. And basically what we've done is we've wired the MQTT library to the Xterm console. And the way this works is that the web terminal can publish and subscribe to the broker, and can publish and subscribe to messages ultimately to the Altair running on the Azure Sphere. So on the Azure Sphere, we've got, in the heart of it, we've got the Intel 8080 emulator. And on top of that, we have the original compiled binaries for Altair Basic and for an operating system called CPM 2.2. And on top of CPM 2.2, we've got Microsoft Basic 80, we've got a C compiler and an assembler, and you can go and build applications. Now, below that stack, we've got Terminal I/O, and the Terminal I/O is responsible for effectively redirecting standard in and standard out from the emulator onto MQTT, across the internet, to the broker, and then ultimately to the web terminal. So that's how the web terminal can talk to the Altair, is via redirected input and output from standard in, standard out on the emulator. Now, what we've also done is a similar concept for the disk. So we provide a B disk, which is read and write, and that's been hooked onto MQTT. And the virtual disk can write, effectively publish onto MQTT topic, and it can read or subscribe to an MQTT topic. And it can send messages backwards and forwards across the internet to the broker, and then ultimately to the virtual disk server that's running in Azure. Now, alongside this, we've got two applications running on the two real-time cores. We've got the virtual disk cache, and that runs a least recently used cache. And the way that the emulator talks to the cache is across the intercore bridge. And we've got another core running some sensors, and they're just monitoring the current environment, the temperature, the pressure, etc. And again, that can talk across the intercore bridge. So that's the overall application architecture. It's made up of 3 tiers: the Azure Sphere, which has got multiple applications on it, 3 applications running on it. We've redirected I/O for terminal, and we've redirected I/O for virtual disk across MQTT, across to a broker sitting up in Azure, and then ultimately to a web terminal. Now, what I'm going to do now is flick across to a device that we've got connected, and I just want to show you just to set a bit of context. So this device here is an open source hardware design, which was originally done by Daniel Carling, and it is available up on GitHub as an open source design. Now, what we have done is we've updated some of the design on that, and we are also publishing that as an open source design. So if you want to go and build your own Altair front panel, you can do that, and it's got all the switches on it, and you can go and it behaves really just like the original Altair. Now, we do appreciate that perhaps not everybody will want to go and build their own Altair front panel. And so we go and look over here on the wiki, and we go and look at Altair setup. You can see that we've got a number of configurations. You can go and run the Altair emulator on just a standalone Azure Sphere device like the Seed Studio or the Avnet devices. And we also have another configuration which is using the micro-click boards. So we've got the micro-click 4x4, which is providing the switches, and we're using the 8x8 LEDs, which is providing the kind of the LED panel from the original Altair. The folk from Microelectronica have built out a really neat Altair 8800 RetroClick, and that's effectively combining the keypad and the 8x8 LEDs onto one board. And of course, that leaves you with another click you can go and do something interesting on. And of course, there's the full-on board that you can go and build. Now, you will find on the right-hand side all the complete instructions about how to get up and running with the Altair on Azure Sphere. And what I'm going to do now is show another device that we've got here. And I'll bring that up onto the screen. Not necessarily the easiest thing to see, I'm sorry, because the light's never that good when you're filming LEDs. So this is the Azure Sphere, the Avnet Azure Sphere device, and I'm running a kind of like a pre-build of the Microelectronica Altair 8800 RetroClick. And what I'm going to do is show you kind of how this all hangs together. So I've got the device there, and I'm going to pop back to the desktop, and I'm going to go across to the web terminal. So what I've got here is the web terminal, and you'll see that I've connected to the MQTT broker. So I put in my device name and I click on connect. And what that's actually going to do is going to connect off to IOT Central. On IOT Central, I enumerate through the devices that I've got loaded for this application, find the device in question that has a display name of Dave's Avnet. Then I go and grab the properties, and I have a particular property that I grab, which is a channel ID. And that channel ID gets used to form a unique MQTT topic chain hierarchy. So that's how the device gets the channel ID, and the Azure Sphere device also gets the same channel ID, hence they can then start talking to each other. Okay, so this is the initial boot up that you would have seen on the Altair 8800. And I'm going to put in the memory. So this is the memory size. So this is 32 kilobytes of memory. We'll go terminal width is 80, and no, we won't bother loading up the cosine features. And we've got Altair Basic up and running. So we've got Altair Basic 4.0. And I can start putting in basic commands. So 2 times 3. And the answer is 6. And I can go and load up applications. So we put in a couple of games. There's tic-tac-toe.base. And we load that up, and it's effectively a noughts and crosses game, really packed from the 70s and 80s. Do you want to go first? Yep, I'll go first. And it's a very basic version of noughts and crosses. And it's a yeah, I won. And you can list out the application, you can go new, etc. Okay, so the next thing I'm going to do is show you how you can bring up the device into CP/M, which is the operating system, as I said, that predates DOS. So what I'm going to do on the device, I'm going to hit the top left-hand corner button up here. And if you keep an eye on that, you'll see it flash up S. And then what it does, it stopped the Intel 8080 CPU emulator. And the next thing I'm going to do is I'm going to press button A. Now this is a shortcut to loading up CP/M. So you'll see that CP/M has come up inside the web terminal. There are a number of ways that you can bring up CP/M. This is a bit of a shortcut, and you'll find more documentation about that in the wiki. So I'm now in CP/M, and I can do a directory. And I've got 2 drives. I've got a B drive. And the B drive is a read-write device, and that is running against the virtual disk drive that's running up in Azure inside a virtual machine. And I can go and erase. So let's go and erase star.star, delete all the files, and you'll see that we've got no files in there. Okay, so the other thing that this file system is doing is, remember, I'm using a least recently used cache of disk sectors that is running on one of the real-time cores. So I actually get really good performance for the disk system, because most of the time I'm actually be able to read the disk sectors out of the core, which has the disk sectors loaded up into memory. Okay, so I'm going to go across to the A drive, and we'll go look at the files in there, and I'm going to pip across. So pip is the copy command, and I'm going to copy across pip.asm. And so that means on the B drive, I've now got this file called demo.asm. And I'm going to fire up a text editor back from the 70s. So again, we've got the binary for that. These are all open source libraries, and we've combined them and put them onto this disk. And I'll fire up, so we're going to do wordmaster demo.asm. Now, wordmaster was a character-based character-based text editor. And the web terminal by default will work in line mode. So what you need to do is press Ctrl-L, and that will put the emulator into character mode. And you need to do that. What's going on is literally every time I move a key, that is sending an MQTT message up to the Mosquito broker in the cloud, and then to the terminal and back again, back to the device. So it's doing a big round trip. But you can see the performance is actually pretty decent. And I'm just going to pop across over here and hit insert. And I'll type in Dave. Hello world, Dave. And then I'll hit escape. And whoops, I've hit another key there by accident. And we'll hit escape. E to exit. Okay, fingers crossed. Not 100% sure about that. We'll have a look at that. Demo.asm. No, that didn't go in. It doesn't matter too much, but you can kind of see I kind of fat-fingered that. Okay, so the next thing I'm going to do is I'm going to assemble that demo file. So I can go ASM, and the file is on my read-write drive on the B drive, and I'll go and do ASM demo. And that's going to assemble that. And the next thing I go and do is I go and do load B, and then that will be demo as well. And if I go and look on the B drive, you'll see that I now have demo.com, so an executable. And if I go and fire up demo, it'll say hello world. How exciting is that? But what's kind of interesting, if we go and type in fact, I've already got the code sitting up the top there. I'm just going to switch out of character mode. Control-L, and you'll see that the code up here, so this is the assembler code that I kind of didn't entirely edit successfully. And you can see what it's going to do is it's going to load this application up at 100 hex in memory. And then it's going to do this thing move immediate, and it's going to load up a register called C, and it's going to put 09 in it. Now 09 is the print function, which is part of CPM. And the next thing it would do is go and load up the address of the string that we're going to print. And if we come across to the string we're going to print, you can see it's going to print hello world. And the way this worked is that it would print the string up to that dollar character. So what I'm going to do now is pop across into CPU mode, and we press Control M. And what I'm going to do now is I'm going to examine the memory at 100 hex. So that's 1 and 4 zeros and another 4 zeros. If I can type that properly. Okay, and you'll see that we're now, I've entered 100 hex, and I'm going to do an examine. And what examine is going to do, it's going to set the CPU pointer to point to address 100 hex. And then what I'm going to do is look at what's there. So you can see at 100 hex, I've got this move instruction. And you remember, if I look up here in my assembler file, there goes my move instruction. And you'll see that it wants to move 9 hex into the C register. So we can see that there goes that instruction. If I go and do examine next, you'll see that there goes on their data bus 09. So this is loading up the call to CPM to go and do a display string on the console. So I'm going to go back to 100 hex, do an examine, and then I'm going to do Control M, which is going to restart up the CPU. And what that's going to do is, because the CPU pointer is pointing at 100 hex, it's going to run the application there, and it's going to run hello world. It's going to run hello world. So we do that, and then we got hello world. Now what you'll find is that because the memory has potentially got corrupted, we may need to reboot CPU on it. And that's the beauty of this, is that what happened, the reason that got corrupted is when the operating system was normally loading up hello world, what it would do is it would load onto the stack the return address. So the application would run, and you'll look at the assembler file, and you'll see the last thing it does is return. Now, of course, when I ran it directly in memory, I didn't load up the return address, so it kind of gets a bit lost. Anyway, you can see you can pretty easily go and reboot up CPM. The next thing I'm going to do is I'm going to pip across to B drive hello world.c. And we will start at WordMaster, and we'll go B and hello world.c. And remember, I need to put that into character mode because it's a character-based text editor, and you can move around and make modifications. Press escape, hit E, enter, and you can make your modifications. So Control L to go back to input mode, line input mode. So on the B drive, I've got hello world. So what I'm going to do now is do C compile. And I'm going to go do CC B hello world HW. And that's going to compile the application. And the next thing I need to do is to link it. So I'll go link, C link B and hello world. And then on the B drive, you will see that there is indeed helloworld.com. And if I run that, and that fires up, and this application just goes around a loop. It was an application I just kind of used for testing. But you kind of see what's going on there, hopefully. To kind of give you an idea how well the disk cache works, what I can do is B drive, copy it across to B. I'm going to copy across mbasic, so microsoftbasic.com. I'm copying that across to the B drive. And I go across the B drive, and you remember this is the virtual disk drive. So I'm redirecting disk I/O over MQTT to a broker that's running in the cloud, and then there's that virtual disk server. Now, of course, what's really happening is because I've got that disk cache running on one of the real-time cores, I kind of bypass that link across to the cloud. So in this case here, if I go and run mbasic, you'll see it runs up pretty much instant. if I didn't have that cache there, it would take maybe 7 or 8 seconds to go and load. And to exit and basically just type in system. So anyway, hopefully kind of gives you a bit of a sense of what you can do. It's kind of a fun project. You can start playing around with opcodes if you want to learn more about how a CPU works. The beauty of the Intel 8080 was it was a pretty simple CPU. It had in the order of about around 80 CPU instructions or opcodes. So pretty easy to kind of get your head around. But as I said, the goal behind this was, one, to create something kind of fun and kind of interesting, but broadly to focus on what you can do around Azure Sphere, particularly around secure IoT, but really kind of pushing the boundaries of Azure Sphere and what you can do. And in this case here, we're using all the resources on that Azure Sphere device, all 3 cores to work together to kind of create the IoT experience. So what I'm going to do here is go back to the, in fact, we'll have a look at the IoT Central page. So this is the IoT Central page up here for the device, and all this information you will find on how to set this up is in the wiki. And you can find kind of interesting stuff about this. So for example, in here, I was kind of interested to see how effective the disk cache was. In this case, you can see I had a hit ratio. I got 526 virtual disk cache hits, and there was 33 disk cache misses. So I can see it's working pretty well. And this kind of disk caching concept can be super useful across a whole range of scenarios. The one that sprung to mind for me was things like retail. You could have a point-of-sale device with price lookup units perhaps being cached. So if some reason you lost your connection back to your central system for your retail system, at least maybe the device could continue to sell items using the cached data about products. That would be one obvious example. Things like maybe you want to do logs. Maybe you don't necessarily need to have the logs written to mutable storage. You might be happy to have that living in memory. So lots of kind of scenarios where you might want to use one of those other cores to offload some of the workload that's happening on the main core. On the overview tab, one of the things I was kind of interested in the memory utilization of what was going on the Azure Sphere. And there are APIs on the Azure Sphere now where you can get at the current amount of memory that's being used. And I plotted that data. It was just kind of useful to find out how the device was behaving. Was it leaking memory or things like that? So it provided a really useful view into how the device is working. You can also go and set properties, start and stop the CPU, set the LED brightness and things like that. There's various views. There's kind of an interesting scenario where you can write a basic app, which can, an Altair basic app, which can reach down into Azure Sphere and grab the local telemetry that's being generated from the onboard sensors, and then read that into a basic application, and also publish that as a device twin back up into IOT Central. So Altair Basic had this kind of concept of input and output ports, and that's how this does. You can kind of break through Altair Basic into the platform, and then we've provided some hooks for various port numbers. So you can't just arbitrarily break through. You kind of break through to known points, and behind those ports, we put some code that will execute and go and do the required function. So you really can kind of cloud enable this Altair in lots of really interesting ways. But as I said, the whole objective behind this is really to kind of drive some creative juices around what you might do with your IoT projects and utilizing all the resources on the device. So I'm going to go back to the wiki page and just really kind of just close off in here. So you'll find on the wiki page all the information for setting up things like IOT Central, how to get the device connected. By default, the device connects to Mosquito, the test.mosquito.org. A caveat on that, the test.mosquito.org is an open public Mosquito MQTT broker. So arguably it's not particularly secure because anyone can look at that data. But what we do have further down in the documentation is how to set up your own private MQTT broker and how to secure that with certificates, which is what you should be doing. And you'll find that, in fact, down in the last exercise, exercise 22 in the wiki. Okay, so anyway, that is the project. It's kind of an interesting project. Do give it a go. If you find issues, then please post issues. Even better still, if you find something or you want to kind of enhance it, feel free to fork it or put in pull requests or whatever you want to go and do with the platform, and have a lot of fun. And hopefully this will expand your ideas as to what you can do around secure IoT and on the Azure Sphere. So thanks so much for joining the session, and good luck.